Welcome to the University of Kentucky's Backyard Streams program. During this webinar, we will explore important fluvial geomorphic concepts related to channel formation and evolution. We will also discuss important stream features such as riffles, pools, runs, and glides. When we talk about fluvial geomorphology, we are referring to the shaping of landforms by running water, particularly rivers and streams. The science of fluvial geomorphology seeks to better understand the many processes that occur with river and stream systems. These fluvial geomorphic processes are centered around the flow of water and the erosion, transportation, and deposition of sediment. An excerpt from the seminal book, Fluvial Forms and Processes by David Nynton sums it up well. Rivers are essentially the agents of erosion and transportation, removing the water and sediment supplied to them from the land surfaces to the oceans. They provide the right ways that carry excess precipitation to the ocean next door, thereby completing the global hydrologic cycle. Despite the fact that less than 0.005% of the continental water is stored in rivers at any one time, water flow is one of the most potent forces operating on the Earth's surface, in terms of both the total energy expended and the total amount of debris transported. When and how sediment particles move depends largely on their size, density, shape, and whether they are cohesive and stick together, such as clay, or are non-cohesive, such as sand. One reason particles move is shear stress. Shear stress, tau, is the force exerted by the fluid or water on the boundary. The boundaries in this case are the stream's bed and banks. It is defined as the product of the specific weight of water, gamma, hydraulic radius, which is often approximated by depth, or d, for wide streams, and slope, or s. The shear stress equation shows that as slope and or depth increase, the ability of water to move sediment also increases. Understanding the factors that control shear stress is critical to understanding why streams erode. Two individuals who made important contributions to the field of geomorphology were Luna Leopold and Thomas Maddock Jr. In their seminal USGS professional paper titled The Hydraulic Geometry of Stream Channels and Some Physiographic Implications, these noted geomorphologists and researchers recognize that the shape of a stream is related to its discharge and hence its drainage area. As seen in this diagram developed by the Federal Interagency Stream Restoration Working Group, several geomorphic features are related to drainage area. The characteristic or bankful discharge, as represented by the dark blue line, increases with increasing drainage area in a predictable pattern. Bankful refers to the maximum discharge a stream can carry before it spills out onto its floodplain. A commonly used definition is this: bankful elevation represents a breakpoint between in-stream and floodplain processes. Important to note is that this definition of bankful refers to channels that are not incised. When channels are incised, they are not connected to their floodplain. Bankfill can be determined for incised streams, although the process is more difficult to do. The same relationship is true for width and mean depth of the channel. As you progress further downstream, that portion of the channel has a larger drainage area, which means a greater amount of runoff flowing to the stream at that point. More runoff means the amount of discharge that a channel receives increases as one progresses downstream. And since the stream has to carry more discharge, it must become larger. The channel increases its size by increasing its width and depth. Other stream characteristics such as slope and bed material size change in predictable patterns with increasing discharge. Interestingly, mean velocity does not change notably with discharge. At play is the relationship between slope, channel size, and roughness. Higher in the watershed at headwaters where the slope is steep, the stream size is generally small. Depths are shallow, widths are narrow. In this case, a large part of the water is in contact with the stream's bed and banks. Roughness or friction slows the water down. Further down the watershed, stream slope decreases and stream size increases. The stream becomes deeper and wider. The percentage of water in contact with the stream's bed and banks is less, meaning that roughness or friction is also less. This intricate balance between slope, channel size, and roughness is the reason bankful mean velocities are relatively constant from headwaters to outlets. The shape of streams or the fluvial forms channels can take can vary depending on the number of factors. One factor is the valley width. The width of the valley to a large extent will drive the physical characteristics of streams that lay within it. For example, the photo on the left shows a wide, expansive valley. Unless altered by man, streams in such valleys have a wide area or floodplain within which they can meander. It is common to find old meander scars, which are the locations of former bends throughout the valley. The stream on the left was straightened many years ago for agricultural purposes. Here, farmers found it easier to farm along straight lines rather than the curves of the stream. The section upstream of the agricultural lands and the tree lines in the distance was not straightened and as such currently has meanders. So let's turn to the photo on the right. The valley for this stream is much more narrow and steep. Also note that the stream shown in this photo on the right is much different than the stream in the photo on the left. The narrower valley width shown in the right photo, as well as the greater topographic steepness of the valley, plays a large role in determining the physical characteristics of the stream. This stream has many small steps, as evident by the white water and small pools. Also notice that the bed material along the edges of the stream is larger. The steeper slope produces a larger shear stress, meaning that small particles are quickly moved out of the system, leaving larger particles which can resist the forces. Those are left behind. Another important fluvial feature is the floodplain. As noted in an earlier slide, shear stress is controlled by slope and depth. When a stream can readily access its floodplain, the depth of water in the channel increases more slowly. This is because a large amount of the water can escape the channel and spread out onto a wide floodplain. The act of spreading a large volume of water out onto the floodplain means depth increases slowly and hence shear stress increases slowly. In essence, the floodplain acts as a relief valve. The photo on the left shows that the stream is well connected to its floodplain. The banks show no signs of erosion. The lack of erosion is due to vegetation and lower shear stress. The stream on the right has a very different situation. For reference, the man in the center of the stream is about 6 feet tall. Notice that the banks are even taller than he is. The stream can only access its floodplain under very large, rare storm events. The amount of stream bank erosion indicates that the shear stress placed on the banks is high. Thus, lack of floodplain access means the stream will continue to erode. Other commonly recognized stream features are meanders as seen in the photo on the left and point bars as seen in the photo on the right. Meanders are curves or bends in the stream. The curviness or sinuosity of a stream is inversely related to its slope. This means that as the slope of a stream decreases, its sinuosity tends to increase. When streams are straightened, their sinuosity is reduced and hence their slope is increased. The slope increases because the stream has to drop in elevation over a shorter distance. This increase in slope results in an increase in shear stress, meaning the ability of a stream to transport sediment, its capacity also increases and hence erosion increases. When trying to decrease shear stress and decrease erosion, it's important to examine the possibility of increasing floodplain access and sinuosity. Now let's turn to point bars. Point bars are depositional features located on the inside of meander bends. In the photo on the right, the point bar is characterized by tan, gravel, and sediment deposits. where vegetation is limited. It's not growing much. Point bars do not form in all streams, but rather are characteristics of wider streams with a larger sediment supply. Some point bars can be quite large, while others can be quite small. In the eastern U.S., it is common for point bars to have vegetation growing on them. Other fluvial forms of interest are steps and pools, as seen in the photo on the left, and waterfalls as seen in the photo on the right. The step-pool sequence is a common occurrence in streams with slopes greater than 4%. Think of steps and pools somewhat like the steps in your house. The steps are usually comprised of larger material such as cobbles and boulders, which can span the width of the channel. These steps separate the upstream backwater pool from the downstream plunge pool. Fine sediments and organic matter tend to accumulate in the pools and behind the steps. In the bluegrass region of Kentucky, step pool complexes are not common as a natural feature. However, some stream restoration projects use them for short distances, especially when dealing with a steep transition or drop. Waterfalls are nick points, which are locations of rapid erosion and incision. At nick points, the stream is eroding to a new or lower base level. We're all familiar with large waterfalls such as Cumberland Falls, which is shown in the photo on the right. Such waterfalls are commonly found in streams, but in a much smaller form. We commonly refer to these small waterfalls as headcuts. One of the biggest aspects of streams we need to understand is the erosion, transport, and deposition of sediment. Streams obtain sediment from runoff from their watersheds or their uplands. Streams also obtain sediment from their bed and banks. The amount of sediment derived from stream beds and banks can be quite significant. Research indicates that stream bank erosion in some instances can account for over 90% of the suspended sediment load in streams. As already noted, depth and slope are important in determining shear stress and hence erosion potential in streams. When stream flow increases during storm events, sediments are sorted in the stream. Coarse sediments are found in riffles. Riffles are the shallow stream features that have some of the steepest slopes. In riffles, finer particles are washed downstream, leaving larger ones. Fine sediments are commonly found in pools along the channel margins or edges and around in-channel obstructions where shear stress is low, meaning slopes are low and/or the depths are shallow. Another point to keep in mind is that biota, meaning fish and macroinvertebrates, are sensitive to sediment. Sediment can clog pore spaces in gravel, thereby negatively impacting reproduction. Sediment can also make the water turbid or cloudy, thus decreasing the ability of fish and macroinvertebrates to see food. Sediment also abrades gills, meaning this abrasion affects respiration or breathing. Streams exhibit a number of depositional patterns such as point bars, mid-channel bars, side bars, and delta bars. The presence of certain depositional patterns is indicative of channel instability. The formation of mid-channel bars means that the channel receives more sediment than it can transport. Mid-channel bars can also form when a blockage is present in the center of a stream. When water hits a mid-channel bar, it is deflected around the bar to the stream banks. Hence, mid-channel bars cause stream bank erosion in their near vicinity. Another depositional pattern common in impacted streams is sidebars. Sidebars may mean that the channel is trying to meander. As water flows downstream, the sidebar redirects water to the opposite bank, causing it to erode. The eroded sediment is then washed downstream. Sidebars are similar to point bars, however, sidebars are not located on the inside of meander bends. Delta bars are common when tributaries enter larger streams. The presence and size of delta bars depends on the sediment contribution from the tributaries. Another important concept in understanding how streams form is dynamic equilibrium, also referred to as quasi-equilibrium. Streams are not static systems. They are dynamic in the sense that they can change or alter their morphology while maintaining stability. For example, many streams migrate laterally throughout their valley. If you look at a plan view of a stream over a number of decades, it is quite possible you can see the stream's many different paths. The important point is that streams experience some levels of erosion and aggradation, but they do so at a rate that allows them to maintain their general dimension or cross-sectional shape, general pattern or amount of sinuosity, and profile or slope without experiencing excessive erosion or aggradation. When something happens in the watershed, such as urbanization, or the stream is straightened, the stream loses its state of equilibrium and goes through an evolutionary process. In the photo on the right, a stream is depicted in patterns showing 1936 in red, 1967 in yellow, and 2005 in blue. The image was developed by the River Design Group. Over the years, the stream has experienced a loss of sinuosity as meander bends were removed. The removal of meander bends produces a steeper stream, meaning shear stress increases and hence erosion increases. When a stream undergoes a change, be it natural such as with a flood, landslide, or earthquake, or be it man-made such as with channelization, the stream will evolve. Two commonly used conceptual models are Lane's balance and a Simon channel evolution model. Click on the links in the PowerPoint to learn more about both. The Simon channel evolution model consists of 6 stages. Cross-section A shows that first stage, that pre-modified stage. When the channel is sinuous and the banks are well vegetated, it's connected to its floodplain. Cross-section B shows a progression of stages 2 through 5. The channel starts going through some sort of modification. Maybe it's channelized, the banks are steepened, it's disconnected from its floodplain. It then goes through the 3rd stage, or degradation. It's rapidly eroding. Then it goes through stage 4, where the degradation also continues, but the channel has downcut and starts to widen out at this point. During stage 5, the stream starts to experience aggradation because it's so wide now, sediment starts to accumulate. And that last stage, which is shown in cross-section C, or that quasi-equilibrium, the stream now begins to reconnect to a floodplain, but this floodplain is now at a lower elevation. The period of time for that channel to evolve through all of these stages can really vary. In Simon's model, where he studied it, he noted it could take 20, 40, or even 100 years for this to occur. To visualize the stream evolution process, take a look at these 2 videos. The first is an M-River straight channel simulation that involves a stream table. In the video, a stream is created, a meander bend is cut off, meaning the stream is straightened, and then the stream starts to evolve as it goes through that remeandering process. The second video, Remeandering of a Small Channelized Stream, shows a graphic in which a stream that once was excavated and widened starts to slowly over time remeander. Now that we have examined how streams evolve, let's look at specific features and their locations within streams. Riffles are shallow features that are located in the straight reaches of the stream in between meander bends for stable systems. For unstable systems, riffles may appear in meander bends. Slopes are steeper and velocities are faster in riffles. As such, bed material in riffles is larger. Pools are the areas of deeper and flatter flows. Located on the outside of meander bends, pools experience slower velocities. As such, the bed material in pools tends to be smaller. In bedrock systems, pool depth is often limited. This photo shows Wilson Creek in Bernheim Forest, shortly after the stream underwent restoration. Notice the pool on the outside meander bend and the riffle located at the bottom left of the photo. In the riffle, the water becomes more rippled or waved. Another feature that is shown in this photo is a glide. Glides are transition features in between pools and riffles. It is in these locations that fish often lay their eggs. In the diagram in the top left, a run is also shown. Runs are located in between riffles and pools. Runs are deeper than riffles but not as deep as pools. Runs serve as a transition between riffles and pools. Many of the bedrock streams in the bluegrass region of Kentucky are dominated by runs. Ideally, a stream should have all four flow regimes: riffles, pools, runs, and glides for optimal habitat quality. The cross-sections of riffles and pools not only differ with regards to shape, but also with regards to average channel velocities. Riffle cross-sections are fairly uniform in shape. The highest velocities and greatest depths are in the center of the riffle. On the other hand, pool cross-sections are generally non-uniform, with one side, the outside of the meander bend, deeper than the other or inside of the meander bend. Hence, the average channel velocity is greater along the outer bend and lesser along the inner bend. As expected from our shear stress equation, erosion along the outer bend occurs while deposition occurs along the inner bend or the point bar area. Channel roughness also affects velocities in the cross-sections. Velocities closest to the channel bed and banks are slower as compared to the center of the channel where roughness has less influence. Another important concept to understand is how a stream's dimensions, patterns, and profile are related. Riffles, as shown in cross-section A to A1, are located in the straight reaches. Riffle cross-sections are fairly uniform in shape. However, pools, which are located in the bends as depicted in cross-section B to B1, are non-uniform in shape. The inside bend is more shallow than the outside bend. As such, the inside bend experiences much less shear stress than the outside bend, and as such, deposition occurs on the inside of the bend. Think of point bars, where erosion controls on the outside bend. Thank you for completing this webinar on Fluvial Geomorphology. To learn more about the topic, check out our publications and additional information sections. For additional information on backyard streams, visit www.uky.edu/BAE/backyardstreams.